I invite Mr. Dr. M.S. Jagdish, the colleague of my department, senior fellow, to introduce Dr. Munish. Over to Jagdish, sir.
Yeah, thank you, Professor Hemant. I just invite all the people to this lecture. Let me have the pleasure to introduce the speaker today, Professor Munish Kansal. Professor Munish Kansal is an assistant professor in Thapar Institute since 2018, and he completed his PhD from Punjab University, Department of Mathematics. His thesis is on some multi-point iterative methods for nonlinear equation and their dynamics. And he has rich experience in this particular field. His research interest extends to generalized inverses, outlet inverses, numerical solutions of nonlinear equations, and system of nonlinear equations dynamical analysis. He has received several awards that includes Best Research Paper Award by UIET, Punjab University, Chandigarh. He also cleared UGC NET with a rank of 62. He is awarded a Junior Research Fellowship by Council of Scientific and Industrial Research with a rank of 44. He is reviewed for many journals that includes one from American Mathematical Society. And he conducted several workshops and published more than 40 papers. It's my pleasure to invite Professor for his wonderful talk on numerical methods in matrix computation and its application. Over to Professor Munish Kansal. Welcome, sir.
Yes, thank you, sir, for the nice introduction. So first of all, I would like to thanks to the organizers, especially Professor Hemant, for giving me the opportunity to present my talk in this workshop. And I welcome all the participants who are in this workshop. So let me just share my screen. Is it visible, sir?
Yeah, it is visible. But some McAfee is projected over there.
One second. Now it is okay, sir?
Yeah, now
fine.
okay.
Yeah, fine.
Okay. Okay. So today I will talk about some numerical methods in matrix computations along with some applications. So in the first half, there were two talks. First one by Professor Soleimani. His talk was related with the nonlinear matrix equations. And after that, Dr. Srivastav put a light on the theory of generalized inverses. So most of the things Dr. Srivastav has covered in his basic lecture. So you might be having some kind of overlapping in my lecture, but I will try to keep it the basics and try to fill in the gaps that was not covered before, right? So basically, during my PhD, I have studied on the development and analysis of higher order iterative methods for solving nonlinear equations. And during PhD, I have figured out one application of scalar nonlinear equations that is in the generalized inverses. So after joining the Thapar Institute, I have started working on this new area that is the generalized inverses. And one student is also doing research in this. So we have published 3 to 4 papers on generalized inverses. So this is also a new topic for me, and we are also learning this topic. And I hope you will enjoy the talk, as I will focus my talk on the very basics of generalized inverse, right? So first of all, what I will do, I will start with the numerical analysis part. That is, just we will recall the methods, some multi-point methods for solving the nonlinear equations, and then how those kind of methods can be used to find the generalized inverses of any arbitrary matrix, right? So let me just start with the introduction. So basically, numerical analysis is a wide-ranging discipline having close connections with various fields of science and engineering. And we know that one of the most interesting and basic problem of numerical analysis deals with the finding the roots of scalar nonlinear equations of the form fx is equal to 0, where f is your nonlinear sufficiently differentiable function defined on some interval I. And second type of problem we have, that is the solving nonlinear systems of the form capital Fx is equal to 0, where f is your vector function from Rn to Rn. Now, these are two important problems in numerical analysis, and we treat them as a basic problems. And these type of problems occur in various that from where we can get these kind of systems or scalar nonlinear equations. So let us consider this second order boundary value problem. So y double dash plus y cube is equal to 0, and boundary conditions are given. Y at 0 is 0, y at 1 is 1. So we want to solve this second order boundary value problem. Now, what do we do in this case? We first partition the domain, that is 0 to 1, into m subintervals, and right, so you have this kind of discretization of the domain, right? Now the points are equispaced, so the spacing I have denoted here by h, and that is equal to the length of the subinterval, length of the interval divided by number of subintervals. So the length is 1 divided by the number of subintervals. So I have divided the domain into m subintervals, so I have h is equal to 1 by m, right? So now at each mesh point, you can define your solution. Let y0 be the solution at u0, y1 is the solution at u1, y2 is the solution at u2, and so on, right? Now, what do? We use the discretization formula for the second order derivative appearing in the equation number 3. So when you use this formula given by equation number 5 and plug it into equation number 3, so what do we get? We get m minus 1 nonlinear equations in m minus 1 variables, right? So we obtain a system of nonlinear equations, and the ultimate aim of numerical analysis is to find out the solution of these kind of solutions of nonlinear equations, right? So this is the first example that we can see that how these systems can appear in different fields of science and engineering. So first example was the differential equation, and second we have some Hemant type integral equation. This is also a well-known integral equation. So if you look at this integral equation, you can see that this is given by equation number 7, right? So when you treat it as a nonlinear system of equations of the form fx is equal to 0, where f is your continuous function defined on the interval 0 to 1, you can see that it can be discretized into system of nonlinear equation with the help of Gauss-Legendre quadrature formula, where it is given by integral 0 to 1 ft dt is approximated with the help of wj f of tj, where what are wj's? These are the weights, and tj's, these are the abscissas, right? So I have taken here for discretization for n is equal to 10, right? And denote xi the approximation of x of ti, right? So when you do this and do the simple algebraic calculations, so what you get a system of nonlinear equations, right? So here aij's are defined like this, and this is based on the definition of the kernel of the integral equation. So again, equations, and we certainly look for some iterative method or analytical method to solve these kind of nonlinear systems, right? So the next question comes to our mind, that how do we solve these kind of systems or scalar nonlinear equations, right? So basically, analytical methods for solving such type of equations, whether it is a scalar nonlinear equation or it is a system of nonlinear equation, that they are almost non-existent, that we already know, right? So there is only one possible choice, that is with the help of approximate solutions, we can actually study the iterative methods based on different iterative procedures, right? So the ultimate aim of numerical analysis is concerned with all the aspects of numerical solution of a problem, whether it is first you develop the theoretical method, then you look at the practical point of view of that method, right? That how the method is efficient. So we ultimately derive some numerical methods to solve these kind of equations, right? So now the iterative method that we generally study, they start with some initial approximation, and then they generate a sequence of approximations which hopefully converts to the desired solution, right? So they are of different types, like for scalar nonlinear equations I'm talking about, these are of two types, you can say broadly. These are of two types. One is one point iterative method, and secondly we call it multi-point iterative method, right? So what is one point iterative method? I will just give you a quick background for this. So the method is said to be one point when the approximation of the required root can be determined only by using the new information at xi, and we don't use any old information, right? So mathematically you can write as xi plus 1 is equal to phi of xi, right? So here phi is your one point iterative function, right? So this is, you have done in undergraduate courses also, that if you choose phi to be x minus f by f dash, then you simply get your one point Newton's method. This is the well-known method that all have studied in the numerical analysis course. Then there is one important family that is known as Chebyshev-Halley's family, right? That is given by this xi plus 1 is equal to xi minus this vector. So you can see here that it involves a free parameter, right? So that is given by lambda. So there is a typo mistake here. This family includes Chebyshev method for lambda is equal to 0, Halley's method for lambda is equal to 1 by 2, and super Halley's method for lambda is equal to 1, right? So this is not alpha, this is equal to lambda, right? So this is a family containing several methods. That how these methods can be used to find out the solution of nonlinear equations, right? So these are the examples of one point iterative methods. Okay, so now let us look at, yes,
A small request, can you make it in presentation mode?
okay,
Because the size may increase.
yes, is it okay now?
Yeah, that's fine. Thank you so much. Sorry for the interference.
No problem, no problem. Okay, so let us now look at the multi-point iterative method. So what do you mean by multi-point? So an iterative method is said to be multi-point if the approximation of the required root is determined only by new information at number of points. Okay, so at different number of points, and the points may not be equal to 1. So and we don't use the old information. That is why we basically call it multi-point iterative method without memory. And if the old informations are used, we call it the multi-point iterative method with memory. But I will not talk about those methods here in our lecture. I will just focus on the methods without memory, right? So this is the general form of a multi-point iterative method without memory. So here we call this phi function to be a multi-point iterative function. Now let us look at one example of this. So I have written Traub-Stephenson's method here. You can see. So here you can see we have two steps basically, where w1 is calculated by xn plus gamma times f of xn, where gamma is your free parameter, it should be non-zero, and this is your first step basically, xn plus 1 is equal to xn minus gamma f square divided by fw minus f of x. So this comes under the category of multi-point method. Then you can have one more option, that is King's family. This is a well-known method, right? So this is a two-step method. You can see here we have first step as Newton's method, and this is the second step proposed by King's. So if you take different values of beta here, you can generate several iterative methods for solving scalar nonlinear equations. So one of the famous method, that is the multi-point iterative method for solving nonlinear equation, is taken with the help of beta is equal to 0, and we call it Ostrovsky's method, right? So Ostrovsky's method is the special case of King's family, you can say. So this is a two-step method. And one more observation here is if you look at this method carefully, so you can see it is using three function evaluations. First is fx, second is f dash x, and then you have f of y, right? So there are three function evaluations. So with the three function evaluations, the maximum order can be 4, right? So this is a fourth order method basically, and that is also confirmed by Kung-Traub conjecture, that says if you have a multi-point iterative method without memory consuming n function evaluations, then the maximum order can be 2 to the power n minus 1. So here we have three function evaluations, so the maximum order can be 4. So it is a fourth order method, and we call this order as optimal order. So this is a optimal method of order 4, right? And in case of without memory methods, we generally focus on developing the optimal iterative methods, right? Now, these iterative methods now are, because they require some kind of initial guess to start with. So given any iterative method, there are if you apply some function to it, so there are many choices for the initial approximation. So in order to study the different initial approximations, Professor Soleimani has also introduced the concept of basins of attractions here. So I will just recall what is the basins of attractions once again to you. Then we will look at two simple examples for it. So in the recent years, the study of basins of attraction of an iterative method, this is a also rapidly growing area of research because it gives us important information regarding the initial points, right? So if you look at this formula given by 11, so you can say that if z star is one of the zero of the polynomial of polynomial pz, and z naught be your initial approximation, then the sequence of approximations generated by Newton's method may or may not converge to the solution. This is, we already know that when you start with some initial approximation, it may or may not converge, right? So in fact, Calais in his paper, he has given the Newton Fourier imaginary problem and recognized that if we already knows the zeros of a function, then Newton's method suggests another interesting problem, that is which starting point converges to which root, and what about those starting points for which Newton's iteration does not converge. And the answer of this problem was given by Julia in 1918. So she demonstrated that the answer lies in the theory of basins of attraction. According to Julia, so basins of attraction of a particular root, or you can say zero of a function, is the set of all starting points z0 which are attracted towards that particular zero. Okay, so more precisely, if you look at this quadratic polynomial az square plus bz plus c, so it will have two zeros, alpha and beta. So if you look at the line which is perpendicular bisector of the line segment from alpha to beta, then when you look at the basins of attraction of Newton's method, when it is applied to the function, so it is divided into two halves. So the left half is corresponding to one root, and the right half is corresponding to the basins of attraction of the other root, right? So let us understand this with the help of two simple examples. First one, I have taken the quadratic polynomial z square plus 1. So it has two zeros plus minus I. So according to the above theorem, you can see that the initial points above the real axis, they will converge to the root z is equal to I, and the points, if you choose below the real axis, they will converge to the root z is equal to minus I, right? So the whole complex plane is divided into two parts. If you pick something from the red region, that will converge to the root iota. If you pick something, some initial approximation from the green region, then it will converge to the root minus iota. So this is how you can basically visualize that what kind of initial approximations are converging to what roots, right? So this is the graphical interpretation of a numerical method, you can say, right? So secondly, you consider the polynomial, say zq minus z, right? So it has three zeros, you can say 0, 1 and -1, right? So the complex plane here, it is divided into three portions with three different colors. So you can see that for z is equal to 0, I have colored the portion with blue. Then z is equal to -1 is corresponding to red. From, let us say, the red region, the approximations are going to converge to -1, and similarly for the others. But here you can see the boundary. There is you can see some kind of disturbance here, right? So what does that mean? That the convergence is not global in this case. That if you pick up something which is closer to, say, -1, it may converge to the green portion also. So this type of picture will give you some idea that how the method is going to behave on a particular problem, right? So because the graphical interpretation is important, so that is why we sometimes study the basis of attraction of a iterative method, right? So now I will try to connect the study of scalar nonlinear equations. As I have already told you that there is a connection of scalar nonlinear equations with the generalized inverses. And up till now, I have just given the recap of the multi-point iterative methods for solving nonlinear equations. Now we are going to shift to the linear system of equations, right? And I will try to give you the background of linear systems of equations and how the numerical analysis for nonlinear equations is connected with the linear algebra. So that I will try to communicate, right? So is there any question till now?
Yeah, and any question for Dr. Manish? No, I think you can proceed.
Okay, so let us start with the linear system of equations. Okay, so from now on, I will just focus on the basics of linear systems. So you might have already studied in your courses or something, some concepts have been discussed by Dr. Shirvastava also and Dr. Faiz also. So there might be some kind of overlapping in those concepts, but still I will just recap all the things again. So you consider the system of m linear equations in n unknowns, right? So the matrix form is ax is equal to b, where you call a as coefficient matrix, x is the vector of unknowns, and b is your right hand side vector. Okay, so now this is the description of linear systems, that we know that the linear system has at least one solution, then we call it consistent. If it has no solution, we call it inconsistent. And if we talk about the conditions, then we know that if rank of the augmented matrix is equal to rank of the coefficient matrix, then we call it the consistent system. And if the rank of the augmented matrix is not equal to rank of the coefficient matrix, then it is called inconsistent system. And further, we say that it has unique solution if the rank is equal to number of the variables, and it has infinitely many solutions if rank is less than the number of variables. So these are the basic conditions that we already know about the existence of solution of linear systems, right? So this is the graphical illustration for the solution of 2 cross 2 systems, right? So I have just taken very simple cases here. Two examples, two equations have been taken, and just I have plotted the graph of two equations. So you can see that they intersect at one point, and graphically that is the meaning of solution, right? So this is a 2 cross 2 system of equations, and this is the graphical interpretation of the solution. Now similarly, you can see in figure 1, we say that if you have these kind of lines in Cartesian plane, so which never meets or don't intersect with each other, then we say that it has no solution. And in picture B, we can see that the lines are overlapping, so we say that it has infinite solution. And in part C, you can see that the slopes are almost close, so the point of intersection is basically difficult to analyze. So we call these kind of systems as ill-conditioned systems, right? So here comes the role of the condition number of a matrix, that if you perturb the coefficient matrix A or the right hand side vector B, then there is if there is the marginal difference in the output, then we say that the system is ill conditioned, otherwise the system is well conditioned. Okay, so these kind of systems we study, right? Then there are different type of solvers, right? So direct methods are also available, and indirect methods, or you can say iterative methods, we already know, right? So in the case of direct methods, we have graphical method that is available for small systems 2 cross 2. Then Cramer's rule, this is one of the fundamental method, very well known to each and everyone. Then we have Gauss elimination method. Then after that we have Gauss Jordan, and then we have LU decomposition. So all these type of methods, these are the category of direct methods. Now for iterative methods, we have Gauss-Jacobi method, Gauss-Seidel method, and SOR method, successive over-relaxation method, right? So basically, the direct methods, they involve the finite number of arithmetic calculations or operations, right? Like Gauss elimination method, it uses approximately n cubed by 3, where n is the order. So when it is getting large, so it is difficult to apply Gauss elimination method. Similarly, other methods, they have their computation complexity. Now to overcome these limitations, we generally go from analytical approach to the iterative approach. And linear equations can be represented by this formula: xk plus 1 is equal to t times xk plus c, where what is t? T is your iteration matrix, and we say that this converges to the unique solution of the linear system of equations if and only if the spectral radius of t is less than 1. So this is the necessary and sufficient condition for the convergence. And if you talk about only the sufficient condition, that is the coefficient matrix should be diagonally dominant. But this is the most stronger condition, that if the spectral radius is less than 1, then you can start from anywhere in the Rn, then the solutions will definitely converge to the iterations will definitely converge to the unique solution. Okay, so for different methods, like for Jacobi's method, you have this iteration matrix is equal to minus of d inverse times L plus U. You can split the coefficient matrix A into L plus D plus U. From there, you can calculate T very easily. Similarly, for Gauss-Seidel method, you can again calculate the iteration matrix T, and then check if the spectral radius is coming out to be less than 1. That is the maximum eigenvalue in magnitude. That is the meaning of spectral radius here. So if that is coming out to be less than 1, then we say that the iterations are definitely converging to the unique solution. So this is the convergence criteria of the iterative approaches. And this is the overall view of all these methods we have studied till now, that what is the stability, what is the precision, and what is the scope of these methods, and how you can implement these methods in MATLAB or any other computer algebra system. So what kind of challenges we have when you implement on some softwares, right? So this is the overall view, that we can see graphical method, the precision is not very good, and the application is limited. So generally we go to some other approach, like we have Gauss elimination with partial pivoting, but again there are problems of round of errors, right? So again we go to some iterative technique like Gauss-Seidel. So again the problem is it may not converge if the system is not diagonally dominant. Again we have to check the spectral radius and so on, right? So but the implementation of Gauss-Seidel in MATLAB is easy. We generally apply this method for solving the linear system of equations if we talk about the indirect methods, right? So there are certain limitations. Every iterative method has its own advantages as well as disadvantages. So based upon the characteristics of the method and based upon the numerical problem, we choose the method that need to be implemented on that, right?
Yeah.
So now let us, yes.
Dr. Manish, one question. Dr. Jagdish, you have a question, right?
Yes, 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 please.
Uh, Jagdish, sir.
No, sorry, I was muted. No, you just shown about the solution. We are discussing about overdetermined system or?
No, I'll come to, I have just taken the
Previous slide.
system, X is equal to B. Now, again,
Previous,
yes, yes. I will now talk about both systems, overdetermined as well as underdetermined. That is coming in the next slide.
Okay, fine.
Yeah, I'm going to discuss that.
Okay, fine. Thank you.
Yes. Okay. So next, let us talk about the solvability of the linear systems, right? So by Dr. Srivastava. So let us consider the system of linear equations Ax is equal to B, where A is your complex matrix of order m cross n, right? So now you can inspect the solution of this linear system by analyzing two things. First one is the coefficient matrix A, and second one is the right hand side vector B, right? So if you know that if A is square non-similar matrix, then the solution can be written as A inverse times B, right? But in case A is your singular or rectangular matrix, then again we cannot apply this solution technique because we cannot find out the A inverse in that case. So there comes the motivation to study these pseudo inverses and generalized inverses, right? Second is we say that if the right hand side vector, that is B vector, that belongs to the range space of A, or you can say column space of A, right, then it has a solution. That is the definition, right? But if B does not belongs to the range space of A, then we say that it has no solution. System of equation has no solution, right? So again, the systems are divided into two portions. We have overdetermined systems and underdetermined systems, right? So overdetermined systems are those systems where number of equations are more than the number of unknowns, right? And in most cases, they have no solution. And if we talk about underdetermined systems, there are more unknowns than the equations, then the systems are said to be underdetermined. And in this case, we generally have infinitely number of solutions. So the previous techniques like Gauss elimination or Gauss-Jordan, we have studied, they are not useful in these kind of cases for overdetermined and underdetermined systems, right? So let us look at one example here. Solve the system of linear equations where A is given to be this and B is this, right? Now, what type of system is this? First question is, then how to solve such type of linear equation, linear system. So how many equations are there? So this is a overdetermined system, right? So this is a overdetermined system. Now, for solving, yes.
Yeah, any question?
Okay.
No question, yeah.
Okay. So basically, approach some other strategy to find out the solution, and that is the least square strategy. That least square solution we find out for these kind of inconsistent overdetermined systems, right? So how does it estimate the solution? So basically, least square approximation that estimates the best fit solution for a system by minimizing the magnitude of the error vector, right? So suppose you have the column space here, or you can call it range space if you like, right? Then you can see if B does not belongs to the column space of A, then it goes outside out of the range space, and you have to find out the minimum vector here, that is the basically the projection vector here, right, such that norm of b minus ax is minimum, right? So if you look for a value of x that comes as close as possible for the solution such that it minimizes the norm of this with respect to some Euclidean inner product, right? So the main aim is to find out the projection of b onto the column space, and from there we can write down the least square solution for solving the equations ax is equal to b. So let me just give you can I write here? One second. Okay, so do you see the screen of OneNote?
Yeah, yes, we can see.
Okay. So let me just give you one simple observation regarding least square solutions. Least square solutions. That how we get that formula. This thing was already discussed by Dr. Shweta, right? So just I am going to recall that concept and try to give you the derivation that how we get that formula, right? So suppose you have the linear system of equations ax is equal to b, okay, and suppose it has no solution, okay. So what is the meaning of this? The meaning of this is we say that b does not belongs to column space of A, right? So if you take A as, let us say, you consider the first column by A1, second column by A2, and so on, say nth column by AN, then you multiply it by some vector x1, x2 up to xn. So that should be equal to b1, b2 up to bn. Bm, right? So A is your say M cross N matrix, right? So what is the meaning of solution of this linear system, right? So we can write it as x1 times first column plus x2 times second column plus on xn times the last column, and that should be equal to the right hand side vector, that is b, okay. So now when you say that this system of equation has a solution, so what is the meaning of that? That you have a choice for xi's. You have a choice of xi's which will satisfy this equation. Or you can say you can take the possible linear combination of all the columns of the matrix A, and that will give you the solution, right? So but when you say that this does not has a solution, what is the meaning of this? The meaning of this is that xi's which will satisfy this equation. There is no choice of xi's which will satisfy this equation. So what do we do in that case? What do we do in that case? If you look at this thing geometrically, so suppose this is your column space, okay. So column space means the set of all possible linear combinations of the columns, and if your b vector is going out of the column space, okay. So what do we do in this case to find out the least square solution? We take the projection of b vector onto the column space, right? So we generally take the projection of your b vector onto the column space. C of A denotes the column space, right? So let us call it some multiple of A. Let me call it AX star. Okay. So now you can see that this is perpendicular to the column space. So basically B minus projection of B onto column space of A, this vector will be orthogonal to, this is orthogonal to column space of A. Is it okay? So if this is the B vector, you can see this vector, whole vector, this is B minus projection of B onto column space of A, and this is your projection if you throw a light on this vector, then you have some kind of reflection in the column space, and that reflection in the column space, that is my projection. This is my projection. Okay, so now this is orthogonal to the column space of A, or in other words, you can say this vector is orthogonal to my row space of A transpose. One and the same thing. If I talk about the column space of A, that is equal to the row space of A transpose. So this vector is orthogonal to row space of A transpose. Now, what is the meaning of this? If some vector is orthogonal to row space of A transpose, that means that vector is in the null space of A transpose, right? That is the meaning of this. That if something is orthogonal to row space of some matrix, then that means that is in the null space of that particular matrix, right? So this vector is orthogonal to row space of A transpose. Now, what is the meaning of this? If some vector lying in the null space, is it okay? Is my screen visible?
Yeah, Dr. Munish, any internet issue is there?
Uh, is my screen visible to you?
No. That sharing is not coming.
Okay, one second. I'm again sharing it.
Okay.
Yeah, one second. Yes, is it visible, sir?
I think this is trying to upload but not coming.
I think my internet is okay. So let me just try once again. Okay. Now, is PPT visible?
Not to me. I think Dr. Svetab, are you able to see? I can't see.
No, not visible.
No, sir. I'm also not able to see.
I think you can rejoin and off your video so that data will be saved.
Okay. Let me just off the video and try once more. Otherwise, I
Because
will
video is also not coming. Video is also not coming.
Yes. I think you can rejoin. That's better.
Yes. I will rejoin, sir. I'm just leaving the meeting and rejoining. Please wait. Yes. Am I audible, sir?
Yes.
Yes.
I have logged in from some other account, sir. So I don't.
Okay, so I think yeah. Yeah, Munish sir. Oops, I think I muted. I think that's why.
One second. Yes, the icon is coming for presenting, but I am not able to present my screen. That is not
Login with
enabled.
Vanitha, right? Okay.
I have logged in with, yes, VS,
Okay.
Vanita Sharma.
Okay. Let me present you.
Yeah.
Okay, now you try.
Okay, 1 second.
Yeah, it's coming. Yes.
Okay. So now you see screen.
I can see the screen.
Okay. So right. Okay. Okay. So yes, sorry for the disturbance. Okay, so let us continue from here. That if some vector is lying in the null space of A transpose, then by applying the definition we get this. So now this implies that A transpose times B is equal to A transpose times your projection of B onto the column space of A, right? And this is equal to A transpose times what you have taken the projection of B onto column space of A, that is A into X star. This is the notation I have given in the starting. Okay, so this implies that your X star is equal to A transpose A inverse times A transpose B. So that is basically the least square solution for solving the linear system of equations. That was also given by Dr. Vastav in the previous lecture. So I have just given the derivation of that how we get that expression, right? So if you look at this result, that if A is a full column rank matrix, then X is called least square solution to Ax is equal to B if and only if it satisfies the normal equations that is given by A transpose A times X is equal to A transpose B, right? And in particular, you can write down X as this, as given in equation number 13, right? So this is called the least square solution of the given system of equations, okay? So now I have given one simple example that will give you more clarity that how to find out the least square solution of a linear system of equations. So I have considered one matrix. This is of order 5 cross 3, right? So the rank of this matrix you can check with the help of MATLAB, or manually you can see that the rank is equal to 3. So the number of columns are 3. So this is a full rank matrix, full column rank matrix, you can see. So using the previous result, that will give you the solution for this linear system of equations Ax is equal to B. So I have just taken these values using MATLAB software. You can also use that. Simply you can take A transpose A into inverse into A transpose B, right? So just plug in the values, you will get the result, right? So this is the solution for the given linear of system using least square strategy. Okay. Now, there are different approaches to calculate these least square solutions. One is through normal equations that we have just studied right now. Then we have QR decomposition. With the help of that, we can also study the least square solutions. And then there is one approach that is very famous one, singular value decomposition. So there are different approaches to calculate least square solutions. So first approach is faster and least accurate among the three, but as generally people use SVD in if you talk about some other fields of science and engineering, they prefer to use SVD. But it is slow but more accurate than the normal equations, right? So now let us talk something about SVD, singular value decomposition. I will just give the brief of that because this thing has already been discussed. So it is a kind of transformation in which the transforming matrices are either unitary or orthogonal. And given any matrix M cross N, it need not be a square matrix. You can always take 2 cross 3, 3 cross 5, and so on, right? So you can always decompose this matrix into product of three matrices, that is U, D, and V conjugate, right? Conjugate transpose. So U and V are your orthogonal, U and V are your unitary matrices. And in real case, you can call them orthogonal matrices and just replace this by transpose. right? And D is your diagonal matrix, whose diagonal contains the singular values of A, right? So singular values are basically the non-negative square roots of the eigenvalues of A conjugate into A. If you calculate the eigenvalues of this matrix, or in real case, if you calculate the eigenvalues of A transpose A and then take the square root, so you will get the singular values. And the D matrix we are talking about here in SVD, it will consist of all singular values of A along the diagonal, right? So now there is certain algorithms to calculate these three matrices, that how you can calculate U, D and V. There are different methods to find out U, D and V. I have illustrated one algorithm here that will give you U, D and V, right? So I will not read all the steps of this algorithm step by step. So just I will try to show this algorithm with the help of one example. So I have considered a very simple matrix here. 2 cross 3 matrix is there. So let us see how you can write down the SVD, right? So the rank of this matrix is 2. You can check. The rank is 2. Number of linearly independent rows are 2. So the rank is 2. So you can calculate A transpose A, right? This is the A matrix, right? So you get a 3 cross 3. Okay, then you can write down the characteristic equation to find out the eigenvalues. That is matrix minus lambda times I is equal to 0. So you get 3 eigenvalues, 0, 2 and 3. Okay, then you have to find out the eigenpairs. That means you have to find out the eigenvectors corresponding to 0, 2 and 3. So these are written over here. These are the eigenpairs of this matrix. Okay, now then write down the singular values of A. What are the singular values of A? If you look at here, so you have to take the square root of that. So that is under root 2, under root 3, and the corresponding vectors are V1 and V2. So you can check the dot product of these two vectors. So they are orthogonal, 1 into 1 minus 1 into 1, that is coming out to be 0, but they are not orthonormal. So you can always orthonormalize those vectors by dividing the vector by its norm. So the first vector you can see here, the norm is under root 2, and then for V2 the norm is under root 3, right? So you can always normalize. So this will be your V vector, V matrix consisting of V1, V2 and V3. So out of 3 matrices, U, D and V. So this is how you can generate your V matrix, that calculate the eigenpairs of or you can say eigenvectors of A transpose into A, right? So this is how you can generate V. Now with the help of V, you can write down your matrix U. Although there is alternative way to calculate U, that is find out the eigen vectors of A into A transpose. That is the another approach, but I have used this different approach, that is with the help of V. Once you have calculated V, you can easily calculate U1, U2, U3, where U1, U2, U1 and U2, these are the columns of U. So that is calculated with the help of this formula, that is AV1 by sigma 1. Sigma 1 is your first singular value. Then U2 is AV2 by sigma 2. Sigma 2 is your second singular value. So you can just do these simple calculations and find out U1 and U2, right? So U1 is your 2 cross 2 and V is your 3 cross 3. Then you have to just adjust the order of the diagonal matrix. So it will contain the singular values on the diagonal. So root 2 and root 3 is there. So in order to satisfy the order, you have to take this column to be 0, right? So this is 2 cross 2 into 2 cross 3 into 3 cross 3. So the order is satisfied. So you can easily decompose the matrix into the product of 3 matrices U, D and V, right? So this is how you can do the SVD or singular value decomposition of a matrix. Now the question is that how this SVD is used to determine the least square solution, right? Or you can talk about the minimum norm least square solution. So if you have a matrix A of order m cross n and B is your right hand side vector containing m entries, then your A DAG B this is the minimum norm least square solution for the given system, right? And this notation is already discussed by Dr. Srivastava. That is for pseudo inverses. A DAG represents the pseudo inverse, right? And he has also shown you the proof that why this pseudo inverse is important, because it gives you minimum norm least square solution. So he has also given you the derivation of this, right? So we will not repeat that again. So let us look at the definition once again. So it basically generalizes the concept of inverse. Because whenever we talk about the inverse, we talk about the non-singular matrices and square matrices. But the concept of pseudo inverse or generalized inverse, you can say, this is applicable for larger class of problems, that the matrix may not be non-singular, matrix may not be square one. So it is applicable to all type of matrices, right? So this is the definition, that if you have M cross N matrix, then the pseudo inverse of this matrix is of order N cross M, right? And if it satisfies the following four conditions, then we call it Moore-Penrose inverse, and the conditions are known as Moore-Penrose conditions, right? So if it satisfies only first equation, we call it generalized inverse or simply pseudo inverse, and it may not be unique. There can be more than one matrix which is satisfying this equation, but if additionally it is satisfying all these three properties, then the inverse is said to be MP inverse, Moore-Penrose inverse, and it is always unique. This is the difference between the simple pseudo inverse and MP inverse. MP inverse is always unique if it satisfies all the four conditions, right? So this is again written here, MP inverse is unique, exists, and it is unique, right? So now there are different formulas available to calculate this A DAG. Like if A has linearly independent columns, you can compute A DAG like this, and if it has linearly independent rows, you can compute A DAG as this. Okay, so I'll just skip the derivation of this. Let us now look at one example how to compute the pseudo inverse for the given matrix. So this is a 4 cross 3 and this is a rectangular matrix, right? So you can check that the rank of A is equal to 3, which is equal to the number of columns. So this is a full rank matrix. So in case of full rank matrix, you can apply this formula, A conjugate into A inverse times A conjugate. And because this is a real matrix, all the entries are real, so you can simply take the transpose, right? So just do these simple calculations. First, I have taken A transpose into A. This is a 3 cross 3 matrix, and this is a square matrix, so you can always talk about the inverse. If you calculate the determinant with the help of any software, it is coming out to be 80, that is non-zero, so this is a non-singular. So we can talk about the inverse of this matrix, and if you multiply by A transpose, post multiply by this, so you get something like this. So this is the pseudo inverse, you can say, of this matrix, right? So this is the simple example that I have taken here for 4 cross 3 example is there, right? And I have applied this first formula because A has linearly independent columns. A has 3 linearly independent columns. That is why the rank of the matrix is 3 here, right? So this is one way. And now there are certain properties, different characteristics of pseudo inverse, right? So like for non-singular matrix, the pseudo inverse is equal to the usual inverse, and again the derivation was already discussed in the previous lecture. And if you take 2 times the inverse, you get the same matrix, and conjugate transpose is interchangeable. And if you look at the product of this, A into A DAG or A DAG into A, these are always idempotent matrices, and A pseudo inverse A into A DAG and A DAG into A, all these matrices have same rank. And the proofs are very simple, 1 or 2 lines proofs are there for this, right? But the important notion here is, like in case of inverse, we say that AB inverse is equal to B inverse into A inverse, but that is not holding here. That property is not holding here. That is AB DAG that may not be equal to B DAG into A DAG. You can check, you can take one counter example where you can see that this is not holding in the case of generalized inverses. Okay. So, is there any question till now? Yes.
Yeah, I think Jagdish sir, you have a question.
Sir, actually, that is about calculating this SVD.
This one.
Just before slide, the previous one, because you are constructing that
This slide.
previous one. No, you are constructing pseudo inverse. Sorry, this U and V. So
Yes.
is it possible to construct like, because sometimes A into A transpose, when you construct it may be less order. The order of A into A
Yes,
transpose and
you
A
can.
transpose may not be the same.
Yes, you can also calculate the eigenvectors of A into A transpose. Then you can generate the matrix U. There is no problem. That is the alternative approach.
Now my question is, suppose you are taking A into A transpose, that order is 2, and A transpose into A is 3. If you do this approach, can you calculate all the vectors?
Sorry, I didn't get your question. You are asking about the order?
Yeah, A into A transpose, let it be 2. A transpose into A is
Yes.
3. So if you
Yes.
compute in this way, whether you can compute all the 3 vectors?
Yes, we can calculate all the 3 vectors. No problem.
If the order is same, it may be, but because here we need U2, U3 in that case.
Because A is your 2 cross 3. So when you decompose A as U into D into V transpose, so U has to be your 2 cross 2. And D has to be your 2 cross 3.
A into A transpose is 3. A transpose into A is 2.
Because U and V are your square matrices. Only you can adjust the order of the diagonal matrix.
Yeah, my doubt is whether this construction is valid when, or it will get the same vector U that we are computing from A into A transpose. That's my question.
So that we okay, I got it. That we have to check. Basically, if A is your I think 3 is your 2 cross 3. So that we need to check with the help of whether we can find out the eigen vectors of A into A transpose, whether they are coming out to be same or not. That thing I'm not sure. I have not done calculations according to that. So we can, yes, we can check whether they are coming out to be same or not. Yes.
Okay, but thank you so much.
Yes. Okay, so these are some of the algebraic methods to compute the generalized inverse. One is through the property by the definition, you can say, and second one is the through singular value decomposition. Okay, so you can calculate a DAG from SVD, like we have studied SVD now. So you can see that how a DAG can be calculated with the help of SVD. So simply you have again M cross N matrix, and this is the singular value decomposition, right? So A DAG will be equal to V times D DAG into U conjugate transpose. Where what is your D DAG? This is simply your taking the reciprocal of the diagonal entries, and the example was also given in the previous lecture. So where the professor Shivastav has given you one example to find out A DAG from SVD, right? So this is the result that we can use to calculate generalized inverse from the singular value decomposition. And you can also cross check all the 4 conditions, that whether it is satisfying or not. So you can check the proof of that also. So that is very simple. Just you need to take care of the matrix multiplications, and then you can cross check all the properties, right? So basically A DAG here it satisfies all the 4 conditions of Moore-Penrose inverse. So this is always unique, right? Because it satisfies all the conditions of Moore-Penrose inverse. That is why this is you can say interesting case also, because of the uniqueness, right? Now these are the proofs of each and every condition. I'm just skipping that because this is simple matrix multiplication, we can also check. And this is another example of calculation. Now let us move to the iterative methods. And now till now we have been talking about the analytical approaches, right, to calculate the generalized inverses, like first through the definition and then through the SVD. Now let us move our attention to the iterative methods, and let us try to reconnect that from where we have started our presentation for scalar nonlinear equations, how they are connected with the generalized inverses. So I have taken here one simple formula that is calculated for finding the Moore-Penrose inverse, that is known as Newton-Schulz iterative formula, and it is of order 2, right? So if you look at this formula carefully, right, so you can see that we can obtain this formula with the help of Newton's method. When you apply Newton's method on this equation, a minus x inverse is equal to 0, and this is the equation that Professor Faz has also discussed in the first lecture, that how the scalar nonlinear equation methods are used to solve certain nonlinear equations. And from this equation we can derive this formula. This is for Moore-Penrose inverse, right? So now similarly there are many other methods like Newton's method. This is of order 2 for calculating the Moore-Penrose inverse. You can see here. Similarly, we have Chebyshev-Halley type methods, right? So this is a third order method. I have written here Chebyshev method is there, some midpoint rule method is there, Homeos method is there. There are certain methods written in the iterative form or matrix form, you can say, which hopefully converts to the MP inverse of the given system, right? So basically, if the given inverse satisfies all the conditions, then we call it MP inverse, and in case only the first condition is satisfied, we call it generalized inverse. If the first two conditions are satisfied, then we call it reflexive inverse, and if first and third condition are satisfied, we call it least square inverse, and if all the conditions are satisfied, we call it MP inverse, right? So these are different basically categories. Some people work in first case, like Shwetab has shown you the derivation of certain method using, I think, first equation and fourth equation, I think, right? So the derivation was based on P1 and P4, right?
P2
so we can yes, P3, I think.
P2
Yeah.
and P4. Second and
P2
fourth.
and P3.
P4.
Yes, yes. P2
P4,
and P3. Yes. So the P4. Yes. So
Yeah.
the derivation was based on these two equations. Yes. Thank you. So again, we have you have seen the definition of generalized outer inverse, that is for given any m cross n matrix, right? So we can talk about the generalized outer inverses of the form which are in the form of xax is equal to x, right? And these are special. Why? Because if we choose some subspace of like this is the Ben Ezrail lemma, right? If T is a subspace of Cn of dimension T and S is a subspace of Cm of dimension M minus T, then A has generalized outer inverse, such that the range space of X is T and null space of X is S, if and only if AT direct sum with S is equal to Cm. So basically, for particular cases from generalized outer inverse, we can get all the other inverses, right? So let us see. Now this is okay. So again, this is another category of generalized inverse, that is known as Racine inverse. So this is the definition, that if A is a n cross n matrix and index of A is k, right, then the matrix satisfying all the three conditions, this is said to be Racine inverse, right? And after that, we have weighted Moore-Penrose inverse. This is another kind of inverse. Some people are working on this direction also. So certain weights are attached to the condition 3 and 4. You can see here. T and S are there. If you take T and S to be identity, then this is simply a Moore-Penrose inverse. But in this case, due to these weights, we call them as weighted Moore-Penrose inverse. And you can say this is the more generalized version. And there are many good papers published in this category also, right? So again, if you choose certain values for T and S, right? If you choose certain subspaces for T and S, and then you can find out your Moore-Penrose inverse, weighted Moore-Penrose inverse, Frasin inverse, and group inverse, right? So these are the different categories that why your outer inverse is more suitable, right? So for different choices, you can get different inverses, right? So now, recently we have done some work on this outer inverses, and for that we have studied one method, three-step method, iterative method for solving nonlinear equations. And you can see how the previous study, or you can say the previous scalar nonlinear equation methods, they can be implemented to find out the generalized inverses, right? So I have considered here three methods, three steps, right? So based on this method, we can actually generate a new method for finding the outer inverse, right? So first step is of Newton like. So here we have different parameters phi, gamma, delta, and these are the conditions here. First two steps are by Corredora et al. And the third step we have taken here, that is of secant type, right? So this is the three-step method for solving nonlinear equations. Now let us see how the study of nonlinear equations that can be helpful to find out the outer inverses, right? So now for solving the scalar equation of the form of this A minus x inverse is equal to 0, and then you apply this formula, so you get the matrix form like this given by 26, right? So this is a fourth order method that I have considered here, right? So the computational time used by the iterative method, this can be minimized if you rearrange the terms and write down like this. So I have written the more refined version here, 27. So it has 4 matrix multiplication at each step, and that will be computationally efficient. So this is the method that can be used to find out the outer inverse, right? So this, you can say there are 4 parameters tk, uk, vk, and xk plus 1, right? So then we have some condition that if the given matrix A satisfies this condition, that is norm of I minus ax naught, that is less than 1, then the iterative family given by this 27, this converges to the solution with the fourth order, right? So this is the condition, and you can say this is the convergence analysis. So what do? We assume that the inequality 28 is true, and let us consider E naught to be initial matrix difference of I minus ax naught, because what do we want to do here? We want to find out the inverse of A. That means A into inverse should be equal to I, but we know that we cannot calculate it exactly. So what do? We take the difference of that, I minus ax naught, right? So that denotes your initial residual matrix. And you can denote ek plus 1 as the residual matrix at k plus first stage. So ek plus 1 is equal to I minus a times xk plus 1. Now you can plug in the value of xk plus 1 here from your formula. This is given over here, right? So you can do this calculation. So after that, you can see you are getting something like this. ek plus 1 is equal to this whole factor 1 by 4 gamma times this, right? So then you can take the norm on both sides. So if you see that when you take norm on both sides and apply the mathematical induction, so you can see that your norm of E1 is bounded by 1, right? And we have also shown it graphically that if you choose the values of your parameter appearing in the family, gamma is appearing in your family. So if it is lying in this region 1/4 to infinity, so you can see from this graph, I have allowed the range to be going to maximum should be 1. Norm of even can go up to 1, right? So if you choose something in this region, then your the norm of even will be bounded by 1, and we know that the errors should be bounded. If the errors are not bounded, the method is not going to converge. So from here we can see that when your norm of ek is less than 1, then norm of ek plus 1, you can apply the induction here, so you will get that is less than equal to norm of ek to the power 4. That is basically the order, right? So when you apply the induction, so you can see that when k is very large, your different initial residual matrix, or you can say after the kth stage ek, they will approach to 0. That means I minus axk, that will approach to 0. Or in other words, your sequence of iterations xk, they will approach to the inverse of the matrix, that is A inverse, right? So it proves that the iterative family 27, this is converging to your inverse, right? So this is first theorem I have written here for the convergence, that it is converging to the inverse, right? Then you can check the order also. So how much time I have left, Dr. Hemant?
You are having, we can go up to the 5, half an hour maximum. Or
okay.
Dr.
Right.
Sultan has a question.
Okay, yes, Shweta.
Yeah. Unmute. Shweta, unmute yourself.
Oh yeah, sorry. Yeah.
Okay.
This is actually very nice presentation. I'm enjoying. I just want to ask one question. Have you applied this method for more Penrose inverse? I mean, for any singular matrix or rectangular matrices, or only for non-singular matrices?
No, I have applied this for singular as well as rectangular matrices. That is the main focus.
Okay,
Yeah.
okay.
I will show some examples at the end of the presentation. I have examples where I think we have this 10,000 cross 11,000 matrix. This is rectangular one. We have applied this formula to calculate this. And I think in the second example where I have taken your partial differential equation, I think this is of the order. This is a square matrix, but this is singular matrix, I think. Yeah, your M matrix, yes. Okay. So I have applied it for different, yes, singular as well as rectangular matrices, yes.
And how about the convergence result? Because this result, I think you have proved for the non-singular matrix. For any general matrix, I mean, slightly change will be there, I think, some on the convergence condition.
This is the, you can see the table here. Yes. You want to see the numerical results?
I'm asking like the convergence theorem that you have just proved, fourth order convergence, that is for the non-singular matrix, right? So I just want to know, I mean, you have done this for this convergence theorem for any arbitrary matrix. So, okay, you have written M cross N matrix.
Okay. No, this is for non-singular, but we have again one more theorem. This one. This is for the general case. This is for the general case. Previous theorem was for non-singular, and
there I think N cross N will be there. I think.
Yes.
That's
so this is the general case.
This is the general case. Right. Now I'm clear. There I think it's N cross N. I think I was thinking that.
Yeah. Yes. Proof I have skipped due to time limitation. There is a proof of this already given in our paper also. So proof is also given.
So you have done for both cases, for the square non-singular matrices as well as rectangular matrices, and outer inverse you have computed.
Yes.
So you have published this work, or it's under construction?
Yes. This is published in Journal of Mathematics and Applied Computing. Springer Journal is there, and we have published it. And it is a joint work with my PhD student Manpreet Kaur. So this is published. Yes.
Okay.
I think another question is there. Sanjay Kalita is there. Sanjay. Yeah, Sanjay Kalita. Can you unmute?
Sorry, sir. I think I don't have any question right now.
Okay, fine. Thank
Yeah. By mistake, it's gone, I think.
Okay, fine. Okay, you can continue, Munish sir.
Okay, sir. Okay. So I think let us now move to the numerical part. So the proof of this generalized theorem, that is theorem 9.1. So I have not included the proof of this, but it is available in the paper. So if anyone is interested, I can share the link of the paper and we can discuss. Anyone can get the reference from that paper, right? So now we have also done some numerical experiments in this paper to validate the theoretical results. So first example, I have taken some random sparse matrix of order 10,000 cross 11,000 and applied the given strategy to find out the inverse, right? So you can see that the first figure shows the matrix, like it is a sparse matrix having maximum entries equal to 0, and the another figure you are seeing here, that is the inverse of the matrix, right? So this is the table, numerical comparison table. So I have taken this stopping criteria xk plus 1 minus xk to be less than equal to 10 to the power minus 11. So I have considered various methods here, and PM gamma, they denote our method for different values of gamma, right? So this is the first column that denotes the number of iterations. Then in the second column, we have computational order of convergence, you can say COC, and then we have residual errors, right? In the this means into 10 to the power minus 7, or this is 10 to the power minus 13, right? And the last column is the running time, or you can call it CPU time, right? So I have taken Schulz method, Smiley's method, Chebyshev method, the methods we have already discussed previously. So this is the numerical results, and we have seen that the new strategies, they provide an attractive algorithm, you can say the approach to find out the inverse, right? So in comparison to the existing methods, and it is comparable also, right? And the second example, we have taken the elliptic partial differential equation. Certain boundary conditions are there. So when you again apply the central difference formula on equation number 35, so you can have certain system of linear equations that is represented by 37. So here you can say your M is tridiagonal matrix, and you want to solve this linear system, right? So we have again implemented our scheme on this linear system. So if I can recall, this is a 35 cross 35 system, and this is a square matrix, but I think this is a singular one, right? So if you apply these certain iterative method, different iterative methods to solve this kind of systems arising in partial differential equations, so we have seen very good results given by the new methods here. You can see in example number 2, this is the numerical table I have shown here, right? And then there are certain other examples, so I have not gone into the detail of this, like this is the image processing examples. This is also discussed in the paper. If you want to look at the detailed numerical results, you can see that paper also. So this is the original image, and this is the degraded image after applying some generalized inverse, you can always get the better picture, right? So in image processing, there is a application of generalized inverses, right? So similarly, you have certain problems in civil engineering also. So this is a statistically determinant trust problem. Everyone is familiar with this. So at each node, we need to calculate the force exerted on the node. So when you try to calculate, there is disturbance from some participants. And
Yeah, I muted.
okay. Okay. Thank you. So if you look at this picture, so at each node we need to calculate certain forces. So when you solve that algebraically, so you always get a linear system of equations, and that is too large, that may be sparse, right? So this kind of problems appear in civil engineering, and again those systems may be singular, so the coefficient matrix should can be singular. So what do we do in that case? We can apply our theory to find out the generalized inverse, right? So again, we have implemented our method number 27 to solve this trust problem, and it gives a very good result on this problem, right? So the different problems from different fields of science and engineering we have tried to incorporate in this paper. So the third example we have also considered from the chemical background. This is some chemical equation, and when you analyze this, so you get pretty large system, right? So you can see here, this is a 12 cross 13 system. This is a rectangular system. So again, whenever we have a rectangular system and we want to solve Ax is equal to B, so we have no other choice. So we talk about the generalized inverses, and again we have applied the proposed methods and tested the existing methods also to solve these kind of linear systems, right? And we have seen the very good results on these type of problems also. So the numerical tables I have not included in the presentation, but yes, the tables are there in the paper. I can share the link of that paper if you want, right? So different problems have been studied to find out the generalized inverse. So there are many applications of this area. So I think that's it from my side. These are some of the references. Again, Srivastava has told the reference of yes, this book, Eddie Ben and Ezrail book. This is the basic book and a very good book on generalized inverses, right? And these are some of the references. So these are the references. Some latest references are there. Some papers have been published on generalized inverse. Professor Soleimani has done a lot of work in this area. So again, I want to say we walk on the lines of Professor Soleimani. Like when I started my PhD, I started with the nonlinear equations, scalar nonlinear equations, and studied by different authors. Then we always look for our expert peers that how they are learning new things and learning new research areas. So accordingly, just we try to contribute a little in that area. So when we see that Professor Soleimani, they have learned and published very good research articles in generalized inverses, nonlinear matrix equations, then we get motivation that we can also study some kind of new stuff. So after PhD, I have started this the concept of generalized inverse after coming here in Thapar. So I'm very new to this area, but we are learning day by day, and one student has already done some work in this area, and she's going to submit her thesis in generalized inverses. So this is my you can say first experience in generalized inverse. I will continue to do work in this. So any collaboration is always welcome if somebody wants to work in this area. So that's it from my side. So if there are any questions, most welcome.
It was a very nice talk from the starting to the different type of iteration scheme and different techniques. Yeah, enjoyable. All the talks were very fine. So before we move to the final things, any question to the Munis or any question to the Sweta also? So because we are at the end, so we can have the question. Yeah, please, sir. You have a question.
Can I ask?
Yeah.
Yeah, Professor Munish, thank you so much. It's a wonderful presentation. A lot of information you have passed, and particularly in this application. And can you just tell me how this generalized inverse you are using? You just mentioned that image processing, but is the basic principle you use? Is it SVD connected or?
No, one is sir. One approach is through SVD. You can also go through SVD, right? But the another approach we are using here. The another approach we are using here is through Moore-Penrose inverse, or you can say outer inverse. SVD is your algebraic method, right? But we are talking about here the iterative approach that is given in 27. Yes, this is the iterative method. So we apply this iterative technique to solve that particular problem. SVD is another approach, that is the algebraic analytical approach that we have already discussed. But I think the iterative methods, they sometimes perform better than the analytical ones because there are certain limitations of analytical methods, and it is not always possible to find out the solution using analytical techniques. Right. So for large size, we come to the iterative techniques to solve various different problems.
Okay. Thank you so much. I just want to have the reference. You told about the book. Can you just show that slide?
Yes, sir. Yes. So this is reference number 8 by Adi Ben Israel and Gribel, Generalized Inverses.
Yeah, thank you. Because in most of the book they will give 2 by 2 matrices and all. 2 by 2 small matrices. I have not seen books with higher order matrices and all. I mean, numerical problems what they have solved. That's what. Hope that this will cover that.
Yes. This is a very good book, as Srivastava has also recommended this book. So I think Professor Solimani will also agree that this is a very good book and basic book for studying the generalized inverses.
Okay, thank you so much. That's all from my side.
Yes. Yes. Thank you, sir. Thank you.
Vellore Mati madam.
Yes, sir. Sir, it's a very nice, very informative lecture, sir. Thank you so much. My concern is, what is the matrix size limitation in the iterative method, sir?
Sir, ma'am, there is no such kind of limitation. We generally have large systems. That is why, because if you can see our first example, so I have considered 10,000 cross 11,000, and it depends upon the specification of your computer also, that how much size it can tackle, because if the processor is low, then you can face some difficulty in CPU time, calculating CPU time. If you are working on some workstations, so it will calculate faster, but there is no limitation theoretically. We are developing methods for any general m cross n, so there is no restriction on the order of the matrix, right? So you can take any large matrix, and that is the main focus basically.
Sir, one more thing. We were talking about this generalized inverse and this Morse-Penrose inverse. So that MP inverse, you said some 4 conditions it will satisfy. That it will satisfy. If it is a NP inverse, you said all these 4 conditions satisfy. So what is the physical application, in the sense you have shown the generalized inverse in the image processing, how generalized inverse is brightening, giving the better betterment in the images.
Yes.
How it is furthermore better if we use this MP inverse methodology? I mean, in the application point of view, I just wanted to infer it. Generally, Ax is equal to B. No? If we find inverse of A into B, will be getting X properly. That is what in general, whatever I understood. So you have given a different perspective. Like if we use this MP inverse, then it will satisfy all this condition. But my view is how that will be enhancing my application, where I'm going to use the generalized inverse. In that place, if I go for this MP inverse, what is the betterment I can get?
Yes. So we have also seen some papers on MP inverse, and I think there is one paper I can share with you after this workshop. So that is based on MP inverse, and in that paper we have also solved these practical applications. So you can compare those two results using MP inverse and outer inverses. Right, so that depends upon problem to problem. Obviously, that depends upon your dimension also. So, but you can still apply other approaches. There is no restriction that we have to just apply the outer inverses. You can go with the MP inverse also. There are many papers available for that. So, because in outer inverse we talk about the two subspaces T and S, and you can say the particular case, that is, but we are talking about the particular domain, right? So that is the more generalized version basically.
Thank you, sir. Thank you so much, sir. One more doubt I have. I think maybe it might be to the sir. I think when we want to find the MP inverse through iterative method, maybe the 3 steps are given, if I'm not wrong. That is, there are 3 steps. In that, some beta can be calculated by considering 1 by norm of A, where A is the given matrix. If A size is very huge, how can we found that? There we need the matrix handling, no?
Yes, I think Dr. Srivastava can answer this more precisely, as he has developed that method consisting of the parameter beta, and as far I remember, he has told that in MATLAB you can choose beta is equal to 1 by norm of A or A square. I don't remember exactly.
Norm
so
of
your question is norm of A. Yes, norm of A. So if A is very large, you are saying if A is very large, so I think maximum norm we are considering there. Maximum norm you are talking about.
Actually, I will say about this. There are some other ways, some other norms also possible to do that. But that Save pointed out, this can be one of the limitations also. Sometimes it's a problematic to compute this because it depends on the eigenvalues. So this is also one thing to work on, you can say. Okay, I mean, something better can be done to this also. But yes, there are some other ways also to do the same thing.
What this LMS algorithm, that least mean square algorithm, they are simply taking that beta value as 1 by lambda max. So if we consider that way, that will support us, sir.
Yes.
Yeah.
I'm sorry, sir. It's not reaching. My signal is weak. I can't hear.
I think they are different type of initialization technique as they are for different purpose they are used in the literature. So we have to choose the which is best one for our method. Accordingly, go with that.
Okay. Yeah. That depends upon problem, and for large systems, you can say for large n, we prefer to use the infinity norm basically, and there is a proof of it also given by Penrose in 1955 that the infinity norm gives you the good solution for large systems. But again, this is open that for given particular problem, there are different strategies to choose that beta. As Srivastav has said, this is again a point of research area. We can also work on that, and that how to improve that so that we get a good choice of beta. That is again an open problem. We cannot say that this lambda max will work better or not. That we have to check.
Okay. Thank you, sir. Thank you so much for clearing all my doubts. Thank you so much.
Thank you, ma'am.
Question? Yeah. I think Gomti, are you here? You have a question, any? I think she is not here. Okay. So if there is no other question, so we can close this talk. I think you can stop sharing. That is.
Okay, sir.
Yeah. So I think everyone can open the video and we can take the one snapshot if possible.
Okay.
Yes. So, Hemant, are you there?
Sir,
Yes. Take the photo if possible for.
sure.
Yeah. So everyone open. Let's try how many photo will come in this screen. Okay. So
Professor Soliman is not.
Yeah, he's
Professor
not.
Soliman.
Yeah, he's not here.
Okay.
Even I can put in all in this classroom. More can be open. Yeah,
you
Salman,
can take multiple pictures.
Yeah, Salman and Saurabh also you can open your video and you join here. Yeah, that's also. So we all in the chair. I think you can also see the same thing, right? You are all in chair.
Yeah, that is a gallery view.
Yeah, gallery view. Okay, fine. I think this is yeah, this is fine. Thank you. So, yeah, so so at the part of last part, there's a vote of thanks. So as a organizer, I want to thanks to all my friends and resource person. So for accepting the talk invitation for this workshop. So this is the first experience of mine, I can say, and it was a good experience to interact with you all and even the participant and full day workshop. It was went well, but with all your cooperation, suggestion meetings. So yeah, so definitely I will plan for big way with all other invited talk with your friends and all whatever we are having with the help of you, because you are expert in this area. So definitely, so I have to contact to you for the future conference or workshop. And I would like to thanks to management for giving this opportunity for conducting this workshop. I would like to thank the Dean, SAS, HOD Department of Mathematics, my colleague, my friends, and the students who are handling outside this, admit the pupil in the team here. So yeah, so even the outside the friend of the VIT who's helping me, making the poster, Dr. Reena Jain from the VIT Bhopal. So I thank you for them making the Google form for me. So yeah, thank you all. And the last the participant, without them this workshop could not be completed. So thank you all. Yeah, so it was rested more, but yeah, joined less. So I was I was surprised even, and feel good. Registration was 220 to 25. Yeah, but here the 70-80 was attendees was there, but it's what a good experience. Hope this will the next time in a big way, and meet you all in personally. So thank you, Munish sir. Thank you, Shwetab sir. Thank you, Jagdish sir.
Thank you. Thank you so
Thank
much.
you very much,
Yep.
sir.
Thank you so much, sir, for introducing the people. Really have great knowledge in this area.
Working from the long time, and now I had to learn from them. So yeah, this is the initialization of this process, I can say. So this was the X naught. This was of one day.
Yes.
We'll converge.
If X naught is good, then we can get the better solution.
Yeah, convergent to some unique solution. Yeah.
So you can plan for a workshop that includes training session also, like
Yeah.
this computation what you are doing, because that needs. We need more support on that.
Yeah. Yeah, so yeah, these people are here, so I think I don't have problem to conduct the new event any. So they are these are the good hand of, and they are having the good people with them. Okay.
Okay.
So thank you to all. I think we can close the session.
Thank you, sir.
Thank you, sir.
Thank you, ma'am.
Thank you
so
very
much.
much.
Thank you.
Thank
Good.
you. Thanks.
Thank you, sir. Thank you.
Professor Hemant,
Okay.
Yeah.
I want to this Vellore madam is a faculty in School of Sense School.
Yeah, I know.
And she's basically BSc in mathematics and then the engineering degree.
Yeah. Okay, that's why it's having the more question, and this is good words of. Yeah, there must be question. Yeah, thank you, ma'am, for joining, and you are having the lightning the verse off with the question. Thank you. Okay, thank you to all. We'll meet you.